All right, so we're going to move on to the conformation of conjugated diene. All right, so I'll give you we use 1,3-butadiene as an example. All right. Also, now butadiene, in short, exists in two forms. So we have S-cis and S-trans. At room temperature, this C2 and C3 bond can rotate. That's why it exists. This compound exists as S-cis and S-trans, right? But the S-cis, I think you might be able to see that have some torsional strain, so it's not as stable than S-trans. So over 90% butadiene prefer as S-trans. Okay, and that's the reason why. So the S-trans is more stable than S-cis conformation. That 12 kilojoule per mole, that's the equal to torsional strain. Okay. Now, what is the 15 kilojoule per mole to convert between S-cis and S-trans? What's going on in here? Well, that's actually the stabilization energy. If you go back, I'm going to go back one slide right here. Oops, couple slides. Here we go, right there. That's a stabilization energy, 15 kilojoule, all right, per mole. Now, why it matters right here? Well, when S-cis and S is converted to S-trans, this happens. The conjugation is broken. All right, so S-cis right here. So this bond have to rotate. See if I rotate 90 degrees, the two p orbitals on the left and the two p orbital on the right are not conjugated. If you remember, the p orbital have to be parallel. If you look at me right here, it have to be parallel. And this is not parallel, which means that the conjugation has been broken, and that causes 15 kilojoule per mole. Okay, and then rotate even more. You 90 degrees further, you will get to S-trans. All right, the 15 kilojoule per mole right here need to be overcome just to break the conjugation. But at room temperature, this 15 kilojoule per mole is easy. That's why I said at room temperature, S-cis and S-trans are interconverted freely. Okay. All right, let's move on to next one. We're going to talk about the molecular orbital theory of conjugated diene.